Hi, this is Lab5 video report. In this video report, I'm going to first do an introduction and then discuss the physics principles, then show my measurements and my computational model and my coding. Then I will answer the reflective questions. So this is the introduction. The purpose of this is to reproduce the situation that is described in Faraday's law, and then collect the data of the bar magnet falling through the aluminum foil tube, and then use the data to model the interactions between the magnet and the aluminum foil tube, and use the computational model to calculate the computational falling time and compare these two times. So in order to do this lab, we need to drop the bar magnet through an aluminum foil tube and then measure the falling time. The measured time is 0.4 seconds, the average measured time. Then the computational model time is 1.26 seconds. So the physics that are involved in this lab are Faraday's law, Brevet-Savart law, and the Newton's second and third law. So we first use the Brevet-Savart law to calculate the magnetic field, and then apply that magnetic field value into our Faraday's law to get our delta T from our computational model. And then we use Newton's second law to constantly update the force and the position of the magnetic bar, and then Newton's third law to the action and reaction pair law to calculate the force that the aluminum foil is exerted on the bar magnet. So here are the measurements. The table shows the falling time for each trail and then the average falling time calculated from each trail. Then there's the mass of the magnetic bar is 0.05 kilogram. The magnitude of the magnetic dipole is also shown, and also the length of the tube, the width of the foil, and the inner radius is also shown in this slide. So here are my computational models. The picture on the left is just a snapshot of the bar magnet falling through the aluminum foil tube. Then the picture on the right shows first the velocity versus time graph of the bar magnet falling through the aluminum foil tube. Then on the bottom of that graph, there shows the computer calculated time. The falling time is 1.268 seconds. So these are some snapshot of my code. The first is the function that I use to calculate the magnetic field of the bar magnet. I copy this code from my Lab3. Then is the function that I use to calculate the EMF, changing flux over changing time. So I write this function based on the formulas that I learned from class and replace the components in that formula with the variables from this code. And then there is functions that I use to calculate the gravitational force on the magnet when the bar magnet is falling. Then I use a for loop to calculate the current and the magnetic force at each ring, since we divided the tube into different rings. So, and then I sum up those two forces to get a net force, and then I update the velocity and the position of the bar magnet at the end. So the computational time, the delta T I got from this code is, as I stated before, is 1.26 seconds, and my experimental value is 0.4 seconds. The reason why there is a huge gap might because I didn't take accurate measurements for the width of the foil tube, because I wrapped the foil tube by myself because I can't buy a well-wrapped aluminum foil tube from the market, so there might be still gap between each layer of aluminum sheet. So that might be one cause of why there is a huge difference between the experimental value and the computational value. So the first reflective question, what if the resistivity of the conductor were reduced as close as possible to zero? I think this would make our magnet take longer time to fall since the current induced on the aluminum foil tube will increase as the resistivity of the conductor decreased. And the second, what if there were holes or slots were cut into the tube? We would lose a segment of L, so the current will be decreased, which means that our magnet will take less time to fall, so it will fall faster.